Welcome back, everybody, to the Python primer for student researchers. Today, we're going to be talking a little bit about interpolation and how we can use the pre-built interpolation programs in the scientific Python packages to do interpolations on your data. So this can come in handy if you need to interpolate between sparse data or if you want to estimate values between known quantities in your data. So let's go ahead and see how this works. So the first thing we're going to do is we're going to import the interpolate, the one-dimensional interpolation from SciPy. So what I'm going to do is I'm going to say from SciPy dot interpolate. This is the library that has all the interpolation programs in it, interpolate. We're going to import a library called interp1d. And this is going to allow us to do linear cubic interpolations on our data. Also, I'm going to need to get my NumPy, because we're going to be using arrays. And then to look at the results that we're getting, I'm going to use matplotlib from what we did last time so that we can see what we have. Okay, so there we've got our three libraries that we're going to import. I'm importing a specific library from SciPy, and we're importing these other ones as NPLT. Okay, so the first thing I want to do is generate some data, right? And this data is going to be some sparsely sampled data off of a known function. So I'm going to set my x values equal to mp.linspace. And this is going to go from 0 to 12. And in fact, since we're going to be using cosines, let's use mp.pi times 4. That's going to be close enough to 12 there. That's going to be 4 pi. And I'm going to take 10 data points. Let's take 12 data points. So what this is going to do is this is going to generate a list, or an array, I should say, of x values from 0 to 4 pi, and there's going to be 12. Okay. And then my y values, I want to get the cosine of those values. So we're just making a sparse list of data here, sparse arrays of data. And if I plot those, just real quick so you can see what those look like, I say plot plt.plot x and y. I get a graph that approximates a cosine, right? So this could be like if you're doing some signal processing, you're measuring a signal coming in and you can only measure it 12 times per cycle. Well, this gives you, kind of a sparsely sampled data. And if we're interpolating, we might want to know what the data are in between some of those values. So let's go ahead and see how we might do that. Okay. So in order to do the interpolation, now that we've got our sparse data set, the first thing we want to do is we want to set an array of values to interpolate to. So this is going to be a finer grid that you can imagine kind of overlays on top of this that allows us to take finer sampled data. So I'm going to call this x new, and we're going to make another array using linspace, and this one's going to go over the same range. 0 to 4 pi, except this time we're going to do 100 data points. And go ahead and we're also going to say endpoint equals true, and that's going to make sure that that we have the endpoint of 4 pi in there. Okay, now we're going to call our interpolation. So I'm going to say I want to interpolate. I'm going to use my interp1d. And I'm going to interpolate x and y, and I'm going to do a linear interpolation. So what this is going to do is this is going to make a new array called interp, which is a linear interpolation of that data x and y. And then if I want to plot what that interpolation looks like, I can pass these values of x new into this new interpolation. So let's see how we do that. I can say plot.plot, and let's first start by plotting our x and y values of our quote unquote data that we created. We're going to call that data. And now let's plot our interpolation. So I say plot.plot, and we're going to plot these versus our x new, and then we're going to use our new interpolated values. So this acts as a function. So this interpolation is acting as a function, which is going to take the values of x new and interpolate the new y values from those x new values. So basically, we're making a new array of y values that's going to be our interpolated values. And we're going to call that our linear interpolation. Okay. And then, of course, because we're good physicists, we put our labels on here. So we have x as our x label, arbitrary units. Let's just call it unitless so that we don't get docked points for not having our units on there. And then this is going to be a function of x in arbitrary units. Okay. And then we're going to put a legend on that. And then we're going to show it. And what I should see here is a graph. What did I do wrong? Oh, whoops. Sorry, this should be plot.xlabel and plot.ylabel. There we go. All right, there we go. So we've got our graph, and you can see that what this has done is this has just done a linear interpolation between those points. So that means that all of these points in here have been calculated to be from the slope of the line between those 2 points. So that's pretty much just connecting those lines. But that doesn't really resemble a cosine function. So what we can do is we can do what's called a cubic fit. So let's go ahead and do that. I'm going to come back up here and I'm going to make a new interpolation. We'll call it interp2. And it's going to look exactly like this one. Whoops. It's going to look exactly like this one, except I'm going to make this cubic like that. And then what I'm going to do is I'm going to add a new line here. I'm going to say plot.plot, and I'm going to add x new, but this time I'm going to use interp2 x new. And this label is going to be equal to my cubic interpolation. Okay, so now I'm going to execute that. And interp2 is not defined because I cannot spell. Okay, there we go. And look at that. So this is a cubic interpolation. So we're not using the sine function. I want to point this out. We're using a cubic interpolation, which is giving us a much better approximation of what this data was called from. So even though we're not using the sine function to generate this, we're getting a sine curve because we're using the data from the sparsely sampled sine curve or cosine curve. And then using a cubic interpolation. And then finally, the last thing I want to do is I want to compare what the cosine actually looks like for that so we can see how close we are. So the last thing I'm going to do is I'm going to graph the cosine. So to do that, I'm going to say plot.plot. And I'm going to say x new. And this time, instead of using my interpolation, I'm going to use the cosine function on those values of x new. And I'm going to say label, we're going to call this the cosine of x. Label equals, just call this the cosine of x. So this is going to add a new graph, which is just the cosine. And I should probably spell that correctly. There we go. So now we're going to be comparing our linear interpolation, our cubic interpolation, and then comparing that to the actual value of the cosine. I'm going to go ahead and hit return, and you'll see that other than some slight deviations at the endpoints and at these major inflection points, which, those are where we're going to have the highest uncertainty, our cubic interpolation is very close to the cosine. Not too bad. All right, so that's how you use the interpolation. And just to kind of review this, what we're doing is this is where we're getting our data from. Right, these could be data from your instrumentation or data from that you've collected yourself. This line right here is generating a much more a finer grid over which we're going to interpolate these data onto. And then these two lines here are doing either a linear or a cubic interpolation, and that's giving us two different interpolations. One that's going to be just using the mx plus b, the other one using a cubic function. And then you call those as functions with your new x value. So this is giving you the new y interpolated values for those new x values. And we do that for the single interpolation, the linear interpolation, the cubic interpolation, and then we're comparing that to the cosine. Put some window dressing on there to make it look nice, and there you go. That's how you do interpolation in Python. Next, we're going to be looking at how to do some other statistical analysis, including curve fitting. We'll see you over there.